Hey there, it's Shannon Magic Myers, and today we will be looking at the inverse of a matrix. So we'll check out properties about inverse matrices, using an inverse matrix to solve a system, encoding and decoding messages using matrices and inverses of matrices, and then elementary matrices and LU factorization. So it turns out I forgot to put a 2.4. So in the workbook here, there's a 2.3 and a 2.5. So we may have a two-parter here. We'll see what happens as it goes. Cool, cool? Let's do it. Definition of the inverse of a matrix. An n by n matrix A is invertible or non-singular. You need to know these words. When there exists an n by n matrix B such that AB is equal to BA, which is equal to the identity matrix of order n, where IN is the identity matrix of order n. It's like deja vu. The matrix B is called the multiplicative inverse of A. A matrix that does not have an inverse is called non-invertible, or what do you think? Beautiful, singular. Okay, notice that this matrix A in the definition was square, n by n. So it turns out that non-square matrices do not have inverses. They are singular. All right, let's look at example 1. For the matrices below, show that B is the inverse of A. Well, one way a person could do that would be to find the inverses and see if they're the same. Or what else could we do? Beautiful. Multiply them together and see if we get the identity matrix. In this case, it would be the identity matrix order 2. All right, so A times B will be cool? All right. Theorem 2.7, uniqueness of an inverse. If A is an invertible matrix, then its inverse is unique. The inverse of A is denoted A inverse. So here that -1 power denotes inverse, not 1 over A. Groovy? Let's check out the proof. What do we know in the premise? Good. The premise states that A is invertible, and we need to show that its inverse is unique. So let's build on that. Since A is invertible, doesn't there have to exist some matrix out there where A times B is the identity matrix, which is equal to B times A? So obviously I want to call it B. So since A is invertible, there exists some matrix B such that A times B equals the identity matrix, which equals B times A. Groovy? All right, let's now suppose that there exists a matrix C such that A times C is equal to the identity matrix, which is equal to C times A. Good so far? Great. So what do we know? We can use this part of the equation from the premise, or from a statement that follows the premise, and we can say A times B equals I. Well, I don't really want things in terms of that. I need to get a C in there. So here, if I multiply both sides by C, and I'm doing this on the left, you have to be very efficient on that. And here we go. So using what? Beautiful. The associative property of matrices. Can't I rewrite the left side as so? And then the right side will actually just be C, because C times the identity is just going to give us C. But what is C times A? Beautiful. C times A is equal to I from here. And then we'll have the identity matrix times B is equal to C. And then what do we get? B is equal to C. So we have shown thus the inverse of A is unique. We tried to find another one out there, and we found out it was the one that followed from the premise. Cool, cool? All right. So next up, we have finding the inverse of a matrix by Gauss-Jordan elimination. And yes, I will have you use Gauss-Jordan elimination, because there's going to be times when there's variables in there that we're using to solve things, and you need to know how to do things by hand. So let A be a square matrix of order n. Write the n by 2n matrix that consists of the given matrix A on the left and the n by n identity matrix In on the right to obtain this matrix AIN. This process is called adjoining, and we've talked about adjoining before. So we're adjoining matrix I to matrix A. If possible, row reduce A to IN using elementary row operations on the entire matrix. Okay, so you got to really keep track of what you're doing. The result will be the matrix, if it's possible, if the matrix is invertible, INA. Good so far? If this is not possible, then A is non-invertible, or, what was that word? You got it, singular. Check your work by multiplying to see that A times A inverse equals A inverse times A equals IN. Groovy? Well, let's do it. Find the inverse of the matrix if it exists by solving the matrix equation A times X is equal to I. Okay? So, here we go. What this means is that A times X equal to I would give us, if we multiplied on the left of each side by A inverse, then what would happen? We would have, good, using the associative property for matrix multiplication, we can group the A inverse times A, and then that would just be equal to A inverse. This would be I times X, which would be equal to A inverse And then we would get the matrix X is equal to A inverse. So what are we going to do here? We are going to find out if there is this A inverse that'll do this. Cool, cool? I need to adjoin A and I what? 2. Beautiful. And so what is that going to equal to? Well, what is A? A is 12, 3, 5, negative 2. And I2 is 1, 0, 0, 1. Cool so far? Okay. Well, what should we do? We need to get rid of the 5 that's in row 2, column 1. Okay. So we're going to have, let's see, what should we do? We could do negative 5, row 1, plus 12, row 2, for a new row 2. Cool so far? All right, well, that'll give us I'm going to rewrite A so that, or I'm sorry. I'm going to rewrite row 1 immediately so I don't mess up and change that. And then our new row 2 will be, well, negative 60 plus 60 is 0, right? And then we'll have what? Negative 15 minus 24 is going to be negative 39. Good. Don't forget to do the last 2. You got to go all the way across. So what will we have? Negative 5 plus 0 is negative 5. And then 0 plus 12 is 12. Good so far? Awesome. So next up, what do you think we need to do? Well, we need to get rid of the 3 that is in the first row, second column, correct? So to do so, we could do 13, row 1. Actually, you know what? That's okay. Yeah, we're good. Plus row 2 for a new row 1 this time. All right? So when we start going on this, we're going to rewrite our row 2 so we keep track of it and don't change it. And our new row 1 will be, well, we're going to have 13 times 12 is 156, because that's plus 0, so we get 156. This one's going to 0 out as per our evil plan. And 13 times 1 is 13. And then negative 5 plus negative 5, so we'll get 8. And then 0 plus 12 is 12. Good so far? Awesome. Okay, so now we just need to do a little bit of housekeeping. Now we just need to get our leading ones, our pivots. So to do so, let's see, we're going to divide or multiply row 1 by 1 156th. And that'll be a new row 1. I'll rewrite my row 2. There's not going to be any change there right now. And our new row 1 will be 1, 0. So 1 over 156 times 8 is going to give us, I think, 2 39ths. Does that look all right? And then 12 over 156 will give us 3 over 39, which further reduces to 1/13. Groovy? And then our last step will be to multiply row 2 by negative 1 over 39 and get a new row 2. And let's see what we get. So we'll get 0 here, 1 here, and then let's see, positive 5/39 here. And then let's see, negative 12/39 would reduce to negative 4/13. Cool, cool? Okay, now be careful because this, a lot of times people say, oh, this is A inverse, but only part of it is. This is equal to I2 adjoined with A inverse, okay? So make sure that you separate it out and say, okay, well, A inverse is going to equal to our 2/39 going across, 1/13, 5/39, and then negative 4/13. And then I'll leave it to you to multiply it out to check your work. Okay? All right. So for the next example here, why don't you try it on your own and see how you do? And then, so pause the movie, try it on your own, see how you do, and then check back with me and check your work. Cool, cool. Good luck. I know you can do it. Okay, let's see how you did. So we need to adjoin I2, right, to A. And that's going to give us 1, -2, 2, -3 on the left. And then on the right, we'll have our 1, 0, 0, 1. So what should we do next? Well, we want to get rid of the 2 in the second row, first column. So to do so, we'll do -2 times row 1 plus row 2 for a new row 2. And then we'll have, I'm going to rewrite our row 1 so we don't make up our own math. It happens to me often. And then our new row 2 shall be. So we'd have -2 plus 2 is 0 as planned. Then 4 plus -3 is 1. -2 plus 0 is -2. And then we'll have -2 times 0 is 0 plus 1 is 1. Cool, cool? So our next operation will be what? Beautiful. We'll have row 2 plus row 1 for a new row 1. So our goal here is to get rid of that -2 that's in the first row, second column. Okay? So we will have our row 2 remains unchanged. And then we'll have row 1, our new row 1 will be 1. And then we'll have a 0 here. And then we'll have, let's see, 1 minus 4 is -3. And then for the last one, let's see what we get. We'll have 0 plus 2 is 2. Cool, cool? So remember, what did we find? We found that this is equal to I2 A inverse. Because if you're able to find the identity matrix on the left side, that means that the inverse is on the right side. And so we get a result of A inverse equals -3, 2, -2, 1. So why don't we check it out, right? It'll be an easy one to check. So A times A inverse would be 1, -2, 2, -3 times -3, 2, -2, 1. So we'll have, let's see, 1 times -3 is -3 plus 4 is 1. And then we'll have 1 times 2 is 2 minus 2 is 0. Now starting on the second row of A, 2 times -3 is -6 plus 6 is 0. And then 4 plus -3 is 1. So that checks. And now let's check A inverse times A. Just remember, they can be different. The products can be different. So here we go. -3 times 1 is -3 plus 4 is 1. Then we'd have a +6 minus 6 is 0. -2 plus 2 is 0. And then 4 plus -3 is 1. So it checks out. Cool, cool. Ready for a 3 by 3? Yes, you are. I'm going to go ahead and be quiet here so that you can speed up the video if you want to. Good luck. I entered in A as itself. We didn't have an A inverse name in the matrix name menu, so I let B equal to A inverse. So first of all, I checked it using the multiplication of the two. So A times A inverse was I3, and B and A inverse times A was I3. And then I just showed you how you could find the inverse on your calculator. You just enter in your matrix A and then use the inverse key. Groovy? All right. So let's go ahead and box our answer here and move along. Properties of inverse matrices. If A is an invertible matrix, K is a positive integer, and C is a non-zero scalar, then A inverse, A to the K, C times A, and A transpose are invertible, and the following are true. So it turns out that A inverse inverse is equal to A. And for the proof of this, we've got all of our conditions here. So since A is invertible, it's part of the premise, right? what do we know? There exists some matrix B such that A times B equals B times A, which is the identity matrix of that order. So what can we conclude about B? Well, by definition, B is equal to A inverse, correct? But what else can we say about B? Well, BA then would equal to, so plugging in A inverse for B, we would have A inverse times A, which is equal to I. So and for B, I plugged in A inverse from this statement here. So A is the inverse of A inverse. Cool? It turns out that A to the K inverse is equal to A inverse multiplied to itself K times, which will equal to A to the inverse raised to the K. Cool? And this third one, the quantity C times A, where C is a scalar, that quantity inverse is equal to 1 over C times A inverse. Groovy? To show that these two are equal, let's take a look at what happens when we multiply the quantity C times A to the quantity 1 over C times A inverse. That'll equal to, good, we can commute the A and the 1 over C, right? So we would end up getting C times 1 over C and then times A times A inverse. Well, that's going to give us 1 times the identity matrix, which is the identity matrix. And we'll just put IN for this one. So that's the first part. What do you think we do next? Beautiful. Other way around. 1 over C times A inverse times CA is equal to, well, again, commuting, we'll have 1 over C times C, and then we'll have A inverse times A. This will be equal to 1 times IN, which is IN. And we're done. Next up, we've got A transpose inverse. It turns out that's equal to A inverse transpose. Groovy? All right, theorem 2.9, the inverse of a product. So this is kind of reminiscent of the transpose of a product. They switch, all right? So if A and B are invertible matrices of order n, then AB is invertible, and AB inverse is equal to B inverse times A inverse, okay? So let's look at the proof of that. Again, we need to show that if we multiply AB not inversed times B inverse A inverse, we need to get the identity. So AB times B inverse A times A inverse is equal to what? Well, we can certainly regroup, right? Because matrix multiplication is associative. So this could be written as A times quantity B times B inverse, and then times A inverse. Cool so far? But what is that? We'll have A times IN times A inverse, which is A times A inverse, which is IN. These are kind of cool little proofs, right? So next up, what do, you think? Beautiful. We take B inverse times A inverse and multiply it to A times B. So again, regrouping, we'll have B inverse times quantity A inverse times A times B. And remember, the reason we can do all this is because A and B are both invertible matrices. So now what are we going to get? We're going to get B inverse times IN times B, which is B inverse times B, which is IN. Cool, cool? We've shown what we needed to show. Use the inverse matrices below for the following problems. Ready? So here, I often have something like this without a calculator, and if you can use these properties often, it makes it much easier, right? So here we go. Isn't AB, that product inversed, isn't that equal to B inverse times A inverse from above? Okay? And we have both of those. Otherwise, we would have had to find the product AB, and then we would have had to go through like that long problem and find the inverse. All right? Because you're going to have to do some of these without a calculator. So then now, let's see what we have going on. This is going to give us 5/11, 2/11, 3/11, and -1/11 times -2/7, 1/7, 3/7, and 2/7, which will equal to, let's see what we get. We're going to have -10/77 plus 6/77, which will be -4/77. Groovy? And then 5/77 plus 4/77 is 9/77. Let's work on that second row, and we'll get -6/77 minus 3/77 is -9/77. And finally, 3/77 minus 2/77 is 1/77. And we've got it. Okay. What about A transpose inverse? Well, here we know A inverse, right? So we could find A and then transpose it and then find the inverse of that. But wouldn't it be easier to use the fact that this is equal to A inverse transpose, right? Well, we have A inverse, so A inverse transpose, we would have, I'll just write it out. So that's what we would have. And then remember, for the transpose, you write the columns as rows. And you'll get -2/7, 3/7, and 1/7, 2/7. Groovy? All right. Next up, quantity 7 times A, that product inversed. Well, using our properties, this is going to be 1/7 times A inverse. Well, don't we know what A inverse is? Remember, it was -2, so we'd have 1/7 times -2/7, 1/7, 3/7, and 2/7. And that in turn will give us -2/49 1/49, 3/49, and 2/49. Cool, cool? All right. Cancellation properties. Now, be careful. People often sort of make up their own math on this. Notice the premise. The premise states that C is an invertible matrix. Okay, it's an if-then statement, so that premise must be true. So this doesn't work for any matrix C, just for invertible matrices C, or an invertible matrix C. So here we go. If A times C equals B times C, then A equals B. That's called the right cancellation property. And then the left cancellation property is if C times A equals C times B, then A equals B. So let's prove that first one. So we have this statement, A times C equals B times C. So since C is invertible, if I multiply on the right of both sides by C inverse, let's see what we get. No pun intended. So this would, we would have had this going on, the grouping symbols. And so then we could move those and we'd have A times C inverse is equal to B times C inverse, which would give us A in is equal to B in, which would give us that A is equal to B. Cool, cool? And the reason we were able to do this is because C was invertible. Groovy? All right, next up, systems of equations with unique solutions, right? If A is an invertible matrix, then the system of linear equations, A times X, matrix X equals the matrix B, has a unique solution given by the matrix X equals A inverse times the matrix B. Oftentimes, in my face-to-face classes, I get the question of, well, can't we just use an augmented matrix to solve systems? And yes, you can, but you're learning all these different ways for multiple purposes. I know that coding, especially coding in MATLAB or Octave, you can simplify something and run the code much faster if you write these solutions in multiple manners. So just kind of go with it, learn how to do all of them so that you've got all kinds of solving systems tools in your toolbox, okay? So let's look at the proof of this. Everything has been defined. So let's just start out with A times the column matrix X is equal to the column matrix B. In our premise, we know that A is an invertible matrix. Okay, so what can we do with that? Beautiful. We can multiply on the left side by A inverse, and then we'll have, using the associative property, we'll have A inverse times A, and then times X is equal to A inverse times B. Well, A inverse times A is the identity matrix times X, which is A inverse times B. So then X is equal to A inverse times B. So that part just gives us the first part, that the solution is A inverse times B. Okay? So now what we're going to do is we're going to take a look at the whole unique thing. All right. So we were able to use this because A is invertible. And then remember that theorem that we had a theorem that says A inverse is unique. Now that was theorem, let's see, I think it was 2.7. So theorem 2.7, uniqueness of an inverse. Ooh. All right. So since you've got this unique inverse, right? Why don't we suppose there exists a C vector, okay, such that this X vector is equal to A inverse times the C vector. So we know A inverse is unique, right? We just need to show what? That the C vector is really equal to the B vector. Cool? Let's do it. So starting with X equal to A inverse times C. I don't have enough room. If we multiply both sides on the left by A, and again, we can do that because A is invertible, right? Then what will we have? We'll have A times X is equal to IN times, this is the column vector C. So then what does that mean? A times X is equal to the column vector C. But what else was A times X equal to? Beautiful. A times X was equal to the B vector, right? So we can conclude what? That C vector equals the B vector, and therefore X equal to A inverse times B is a unique solution to A times X equal to B. Now, that concludes the proof, and it's pretty powerful. And what I usually compare it to is the equation of a line. So you know how there's different forms of the equation of a line. You can have the point slope form, you can have the general form. So let's just put kind of a note here, all right? Let's consider equations of lines. Right? So if you think about that, aren't there different forms? I mean, you can have y minus y1 is equal to the slope times x minus x1. You can have a times x plus b times y plus some c is equal to 0. Or this form, y is equal to m times x plus b. This is the slope-intercept form, and that's the only form of the line for the equation of a line which is unique. But the others are not. And so that's that's what makes this thing special. And right along, cryptography. This is always very fun. This is very basic. All right. So cryptography, a cryptogram is a message written according to a secret code. Suppose we assign a number to each letter in the alphabet. So 0 would be assigned to a space, 1 would be assigned to A, etc., all the way down to 26 being assigned to Z. Now, let's look at example 5. we want to write the uncoded row matrices of size 1 by 3 for the message target is home. So what do? Row 1 would end up being what? So we're doing 1 by 3s. So what's the T? What number correlates to T? Beautiful, 20. And now we need the A. And then what? R is 18. Good. See where I'm going? That's TAR. And then now I'll do my next row matrix. So I'll just work on this quietly so we can speed it up. You go ahead and try it on your own. All right, how'd you do? Awesome. Okay, so I highlighted the corresponding letters so you could see what statement we made or sentence we made. Okay? Now what we do is this. We're going to use this information and the given matrix. So it would just be any invertible matrix that you would use. The more secure that you want your message to be would be the size of the invertible matrix that you pick. So you could do a 6 by 6, right? You could do a 16 by 16. And what would change is that your row matrices would be adjusted. So for a 6 by 6, you would have rows of size what? Or dimension would be 1 by 6 instead of 1 by 3. Cool? Okay, so in order to encode that message, all right, what we're going to be doing is we're going to be multiplying each of our rows to this matrix A, and we'll get this other result, call it, I don't know. Okay, so we have our row matrices for reference. Let's do it. So we first want to do our 1 times matrix A, and so we'd have 2118 times matrix A, which is 1, negative 2, 2, negative 2, negative 1, 1 and 3, 1, negative 1, and negative 4. That's going to result in what? We have a 1 by 3 and a 3 by 3. So we're going to end up with a beautiful 1 by 3. So I'll let you do the computations of each of these. And you just let me know how you did. Okay? So how'd you do? Awesome. Now, what would happen really is that a lot of times you would just see a series of numbers, right? So, I mean, here you could just write all of these numbers across or whatever. They wouldn't be in matrices. They might be page numbers they had to look up or something. I don't know. But so your end result then, you know, you could look at like, oh, okay, I might just have 37, negative 57, negative 109. And so you might just see a series of numbers like this. Cool, cool. And then you'd also want to know how to decode the message, right? When we encoded, what did we do? I mean, we did Ri, right, for some I, times the matrix A was equal to the corresponding Di. That encoded our message. What about decoding the message? Well, wouldn't we want to isolate Ri? So let's check it out. I mean, we had this Ri times A equals Di. And what if we multiplied both sides of this equation by A inverse on the right side? That's going to give us Ri times A inverse equals Di times A inverse, which gives us Ri times In equals Di times A inverse. So Ri equals Di times A inverse. That's why it's in that order, right? That's how you noted that the Di is on the left. Cool, cool. And so this decodes our message. That wraps up part 1 of this section. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell all of your friends to subscribe as well. Bye.